Let's take a look at an example problem that allows us to connect position, velocity, and acceleration of a particle. So here's the problem. We are given a particle's position on the x-axis by a function x of t, which is equal to t to the third power plus t to the second power minus 5t minus 5. It's important here to note that t is in the real numbers and it's measured in seconds. So this means that t can take on any value, positive or negative. In a problem like this, we're going to have multiple questions that we're going to answer later on, but they're all going to have to do with position, velocity, and acceleration. So the first thing we'll do is we'll find the functions that are going to represent the velocity and acceleration. Given the position of the function x of t, to find the velocity of the function, we're going to take the derivative because the velocity is the rate of change of the position. So we're going to say that the velocity with respect to time is going to be the derivative of x of t, which will be 3t squared plus 2t minus 5. And I probably should have written this down here. The velocity is equal to the derivative of the position function, so I'm just going to write that in here. Now, to find the acceleration tells us how fast the velocity is changing. So the acceleration with respect to time is going to be the derivative of velocity, and that's going to be 6t plus 2. Now, one of the most important things that we're going to do here is we're going to figure out when each of these is equal to 0. And to do that, we're going to factor them. You may note here that the position function has already been factored for us, at least to an extent. We could factor this further as a difference of squares, as t plus the square root of 5 and t minus the square root of 5. But that's going to allow us to solve for 0 very quickly. Let's also factor the velocity function here. So the velocity function is going to be equal to 3t plus 5 and times t minus 1. And that's going to be very useful for us here when we go later in the problem and we want to figure out when each of these is equal to 0. So let me get some of this stuff out of the way here. So now that we know what the functions for the position, velocity, and acceleration are, it's going to be useful to know when each of those is equal to 0. So we'll set each of those equal to 0 here real quick. We know that x of t is going to equal 0 when either of these factors is equal to 0. If we set t squared minus 5 equal to 0, we get t equal to plus or minus the square root of 5, which is a number that's a little bit bigger than 2 or a little bit smaller than negative 2. And we also get x is equal to 0 when t is going to equal negative 1. We'll get the velocity equal to 0 when we set each of these factors equal to 0. So if we set 3t plus 5 equal to 0, we get velocity equals 0 when t equals negative 5/3. And we also get velocity equal to 0 when this factor is going to equal 0, and that's going to be when t equals 1. And then finally, it may be useful to know when the acceleration will equal 0. So that's going to happen when this 6t plus 2 equals 0. And we get t equals negative 1/3. In addition to knowing when each of these functions is equal to 0, it's also going to be useful to know when they're positive and when they're negative. One thing that's really useful in this problem is to note that each of these functions is a polynomial, which we know is going to be continuous. And so we know that the sign of each of the functions can only change when the function equals 0. So we know that the function's not going to go from positive to negative unless it crosses through 0 first. So what we can do here is we can make a little chart and figure out where each of the functions is equal to 0, and then we can just check regions, and we know that the value is going to stay positive or stay negative within the entire region between the zeros. Okay, so we have a chart here for each of the functions, position, velocity, and acceleration. Notice that for the t values, I've plugged in each of the values of t where each function equals 0. And then I've also left a region that we can test to see if the function is going to be positive or negative within that region. So this region here, we could write it in if we wanted to. I'm going to leave these blank for now. But that's going to represent the interval from negative infinity to negative square root of 5, not including the square root of 5. And we could write those intervals in between each of the points, but I'll leave that to your imagination for now. We do know that the position function is equal to 0 at negative square root of 5 and at negative 1 and at the square root of 5. And what we want to figure out is if it's going to be positive or negative in between each of those zeros. We know that it has to be one or the other. These are the only 3 zeros for the function. And we know that it can't change within the region. So we know that from negative infinity to negative square root of 5, it has to always be positive or always be negative. If we plug in a large negative number, say negative 100, into our function here, it's actually a lot easier to do in the factored form. Let's say we plug in negative 100, we're going to end up with a big positive number here and a negative number here. We know a positive times a negative is going to give us a negative. That means that the function, the position function, is going to be negative when t is less than negative square root of 5. Now when we get to negative square root of 5, the position function takes on the value of 0, so that's a potential place where it could change signs. If we know a little bit about how polynomials work, we could guess at what's going to happen here, whether it's going to stay the same or switch. In fact, since there's only one root or one 0 at negative square root of 5, we know that it's going to switch. But let's go ahead and check a value. I do know that negative 2 is between negative square root of 5 and negative 1, so I'll try negative 2 here in this function. Negative 2 squared is 4, minus 1 is negative 1. Minus 5 is negative 1, and then negative 2 plus 1 is negative 1. So we have a negative times a negative, which is going to give us a positive. And continue to try points in each region. We can plug in 0 here and see what happens. We end up with a negative, and we can plug in any large number, any number bigger than the square root of 5, and it turns out that every t value greater than square root of 5 gives us a position that is positive. Doing the same thing for velocity, we can plug in a negative number into the velocity function. Again, it's easier to do into the factored form. If we plug in a large negative number, we'll get a negative times a negative, which is positive. That tells us our velocity is positive in that region. We do know that the velocity is 0 at negative 5/3 and at 1. If we try a number between negative 5/3 and 1, say 0 for t, we get a 5 and a negative 1. That's going to give us a negative. So we know the velocity will always be negative on the region from negative 5/3 to 1. And plugging in a large number, we get a positive velocity in that last region, at any t value where t is greater than 1. And moving on to acceleration, we know the acceleration is 0 at negative 1/3. And it's fairly simple to check regions here. Plugging in a large negative number, we get a negative to the left of negative 1/3, and we get a positive to the right of negative 1/3. One more thing that we'll want to do before we go start answering questions is to compile all this information we've gotten into one chart, and that'll allow us to see what's happening with position, velocity, and acceleration at any given point. So I'll go ahead and make a chart here, and in our new chart we're going to use t values to separate intervals at each of these places where any of our functions might equal 0. So we're going to have intervals separated at negative square root of 5, negative 1, square root of 5, negative 5/3, 1, and negative 1/3. and then we will check regions in between each also. And essentially what we're doing is we're going to combine all of our information from these charts into one big chart. So our goal at this point is to fill in our chart here. Notice that in the chart I have t values. As time goes on, we're going to check what happens at each value. We have values for position, velocity, and acceleration. And the values that I have put into the chart here are the values when any one of those functions, position, velocity, and acceleration, might equal 0. So looking at our charts here, I see that the position is equal to 0 at negative square root of 5, negative 1, and the square root of 5. So I'm going to put zeros in my chart for position at those places. And I also note that the velocity function is equal to 0 at negative 5/3 and 1. So I will put zeros in the chart in those positions. And finally, the acceleration is equal to 0 at negative 1/3 here. So we know from our chart here where each of the functions is equal to 0. We also know the regions in between those points, whether the position, velocity, and acceleration are positive and negative. So what we can do is fill in the values from the charts here. I know every t value, at every t value less than negative 5, that the position is going to be negative.
Morning.
Good morning. Now, looking at this region between negative square root of 5 and negative 1, we know from our chart here that the position function is going to be positive on that entire region. So we know that it's going to be positive on all values there. It can't change to negative, and it can't be 0 because we know there aren't any zeros in between. And likewise, we know that it's going to be negative everywhere from negative 1 to the square root of 5, and then it's going to be positive to the right of the square root of 5. We can fill in the other rows in a similar way, just looking at what we have in the charts up here and filling it in here. And so what we have here is a completed sign chart that tells us that any point in any interval, whether the position, the velocity, and the acceleration is positive, negative, or 0. At this point, answering each of the questions is just a matter of interpreting the signs of the graph. And so let's go ahead and do that. When is the particle at the origin? That question is asking when the position is equal to 0. So the particle is going to be at the origin anytime x equals 0. So this is going to be when t equals plus or minus square root of 5, and also when t equals negative 1. When is the particle on the positive x-axis? Well, the positive x-axis is just when the position is positive. So it's going to be when t is in the interval from negative square root of 5 to negative 1. And then x is also positive to the right of the square root of 5, so from the square root of 5 to infinity. When is a particle on the negative x-axis? That's going to be any time that x, or position function, is negative, so it will be on the negative x-axis on the interval from negative infinity to negative square root of 5, not including this negative square root of 5, and also on the interval from negative 1 to the square root of 5. Next question, when is the particle at rest? The particle is at rest when the velocity equals 0, so it's going to be at rest here and here when the velocity equals 0, so at t equals negative 5/3 and when t equals 1. The particle will be moving forward when the velocity is positive, so it's going to be moving forward in this region and in this region, so from negative infinity, so on the interval from negative infinity to negative 5/3, and velocity is also positive, so the particle is moving forward on the interval from 1 to infinity. And the particle will be moving backwards when the velocity is negative, so that will be on the interval from negative 5/3 to 1. Also note that we are not including the endpoints because the velocity is equal to 0 on the endpoints. Alright, when is the velocity constant? Well, the velocity is going to be constant when the acceleration is 0. That means that the velocity is not changing. So the velocity is constant at t equals negative 1/3. The acceleration is positive. That's fairly easy to see in the sign chart here, everywhere to the right of negative 1/3. So it's going to be positive on the interval from negative 1/3 to positive infinity, and it's going to be negative when the acceleration is negative in the chart from negative infinity to negative 1/3. Next question, when is the particle moving toward the origin? Well, the particle is moving toward the origin when it is to the right of the origin and moving backwards, or to the left of the origin and moving forward. So that means that it's going to be moving toward the origin anytime the position and the velocity have different signs. So anytime the position and the velocity have different signs, it's going to be moving toward the origin. So if we look here, it's going to be moving toward the origin here because we have position and velocity are opposites. So it's going to be on the interval from negative infinity to negative square root of 5. Here on this interval they have the same sign. Here they have the opposite. So they'll be moving. It will be moving toward the origin from negative 5/3 to negative 1. Here they have the same sign, and here they have the same sign. Here they have different signs, so it will be moving toward the origin on that region from 1 to the square root of 5. It will be moving away from the origin when the position is positive and the velocity is positive, or the position is negative and the velocity is negative, and that actually turns out to be the inverse of the regions that we just found. So that's going to be from the negative square root of 5 to negative 5/3. Okay, that during that region the position and velocity are both positive. Also on the region here where both are negative, and that's going to be from negative 1 to 1. And then also to the right of the square root of 5, they are both positive, so it's going to be the square root of 5 to infinity. When is the particle speeding up? The particle will be speeding up when the velocity and acceleration have the same sign. So if the velocity is positive and the acceleration is positive, then the particle is going to be speeding up. And that's going to be the case here on this region from 1 to infinity. And it's also going to be speeding up when they're both negative, when the velocity is negative and the acceleration is negative. So it's speeding up on the region from negative 5/3 to negative 1/3. Because in that region they're both negative, and it's going to be speeding up on the region from 1 to infinity. And conversely, the particle is going to be slowing down when the signs are opposite for velocity and acceleration. So, the position will be slowing down when the signs are opposite. Velocity is positive and acceleration is negative on this interval from negative infinity to negative 5/3. And the signs are also opposite on this region here from negative 1/3 to 1, where the velocity is negative and the acceleration is positive. That means it will be slowing down on that region also. And that's it.